examples involving making number codes. Right. This table is there simply to give you a direction in terms of times when you are coming up with number codes. They might be there to meet certain conditions, and divisibility rules are important. So that I'm not going to read through everything, but I'm simply saying this is important for you to know, so that if I'm simply to refer to 2, which we are going to use, we are saying a number is divisible by 2 if the last digit is 0, 2, 4, 6, or 8. That means once we have a number with the last digit, any of these digits, then we can conclude that that number is divisible by 2. So these are some of the rules that you are supposed to know, so that at some point you can apply them as you answer questions to do with number codes. Right, let us look at this problem. The digits 0, 1, 2, up to 7 are used to make 4-digit codes, right? Now, the question is, how many unique codes are possible if the digits can be repeated? So we need to answer that. Then B, how many unique codes are possible if the digits cannot be repeated, right? C, in the case where the digits may be repeated, how many codes are numbers that are greater than 2000 and even? Number D, what is the probability that a code will contain at least 1 7? The digits may be repeated. Number E, what is the probability that a code will contain at least 1 7? The digits may not be repeated. So you find that D and E, we are looking at the same situation, but where digits may be repeated, and in E, where digits may not be repeated. F, how many codes can be formed between 4,000 and 5,000? The digits may be repeated. Right, let us give solution to our problems. We start with A, how many unique codes are possible if the digits can be repeated? Right, we note that from the digits given in the problem, we start from 0 to 7. So to know how many digits are there, you can use the idea of counting without counting. That is 7 minus 0 plus 1. You get 8 digits, right? But what we want is to find 4 digits codes. Repetitions are allowed. We are going to use these digits, right? 0 to 7. So as such, you'd see that this is a situation of a subset. That is 4-digit codes. We are taking them from 0 to 7. So the 4 digits are a subset of the digits 0 to 7. So in essence, we only have 4 places to fill the 4 digits, repetitions allowed. So the first position, any of the 8 digits can occupy that, right? Once that is done, since repetition allowed, so any of the 8 can occupy second, third, and fourth. That is the understanding, right? Therefore, by the fundamental counting principle, we are simply saying the possible 4-digit codes is 8 times 8 times 8 times 8, which is 8 to the power of 4. This can be simplified to give you 4,096, right? So we have given solution to the problem, right? Then we go on to B. How many unique codes are possible if the digits cannot be repeated, right? It's the opposite of what we did in A. Now we don't want to repeat the codes as you are seeing here. So in essence, all what it means is we are going to come up with the 4 places, but we are saying the first place, any of the 8 digits can occupy that. That is, there are 8 choices. Once this is filled, I'm left with 7 digits. Once this is filled, I'm left with 6. Once it's filled, I'm left with 5. So that should be the understanding of no repetitions. Once a place is filled, then you subtract, right? So as such, these are numbers representing various choices on various positions, but together, then that's where we apply the fundamental counting principle, 8 times 7 times 6 times 5, right? So the possible 4-digit codes are given by that, which can be reduced to that. So that's the solution to B, and it's not the same as in A, because in A, repetitions were allowed. In B, no repetitions. Let us look at C. If the case, in the case where the digits may be repeated, how many codes are numbers that are greater than 2000 and even, right? Here, when you interpret the meaning, you should be very careful. We are saying numbers that are greater than. There is no equality here, strictly greater than 2000. And those codes should be even, right? So we start now to try to check on the conditions. How are we going to satisfy them? Here are the 8 digits, 0 to 7, right? A number is even when it's divisible by 2. We are trying to attend to this condition. So once a number is divisible by 2, it is even, right? Then from the initial table that I showed you, a number is divisible by 2 if the last digit is 0 or 2 or 4 or 6 or 8. That is what it simply states, right? That's the rule, right? Once this is done, then now we can actually choose from these numbers that we have in our 8 digits, because 8 is not a part of our digits, so we cannot work with it. Therefore, so we have 4 digits, right? From here, that is 0, 2, 4, 6, to put at the end of the codes for it to be even, because we know that any number is divisible by 2 when we have these digits at the end, right? But the fact that this is divisible by 2, it will be even, right? So we have this, right? Then we are done with that. Then now the fact that we want the number codes to be greater than 2, to give us a number greater than 2000, we are saying, let us now check the digits that can start to give us codes that will be greater than 2000, right? So we have 6 digits greater or equal to 2. That is, in the digits that we have here, we have the 2, 3, up to 7, right? Then if ever we have the other 3 to have the 4-digit code, we are saying these are the ones that are supposed to start, because we'll be assured that we can get a code greater than 2000. But I've included the equal to 2. you shall see why if I include the 2, yet we are saying greater than 2. Right. The 4-digit codes greater than or equal to 2000 and even repetitions are allowed. I've put the greater than or equal to 2000, right? And even. Why? Because at the end of the day, this 2000 shall come up because of the reason that repetitions are allowed. That is to say, here is the 4-digit codes. That is, we are saying first, the 6 digits greater or equal to 2. These 6 can occupy the first position. So I have 6 choices. That is, it could be a 2, a 3, a 4, a 5, a 6, a 7. Right? Then at the end, for the code to be even, I have 4 choices. Right? It could be 0, 2, or 4, or 6. Right? So I've filled the first and last, but I cannot remove them for reasons that repetitions are allowed. Therefore, for the second position, I'm still choosing from the 8 digits. The third, the same from the 8 digits, right? Understanding that then, that will mean the fact that I've said 4-digit code greater than or equal to 2000. I'm simply saying I can have a 2000 as a code. How? Because on 6, the 2 is there, so it can occupy there. Then obviously, since the repetition are allowed, and again, the 4, the 0 is there, so the 0 can be here, then here we have the 0, 0. So we have this 2000 as a code, which is even. So we are saying we need to exclude this because the question is saying codes are numbers that are greater than 2000. So we need to remove this at the end of it all because it is included, right? So the 4 digits codes greater than or equal to 2000 and even, we obtain them by multiplying 6 times 8 times 8 times 4, which is what I have here. And this is the reduced number, right? 1536, right? Now, why have I said greater than or equal to 2000? It's because of this reason to say 2000, if we remove the 2 totally from the possible 6 digits greater than or equal to 2, we remove the 2. That means we are not going to have any digit which will contain the 2 as its first. But check this, 2010 is a number greater than 2000. So this is the only approach you can make to make sure that you don't miss such numbers. There are many, because at the end, we have put 0, but I've put just 1 here. I can put even 7 here, but still there are a lot of them. So for you to avoid a situation where I'm going to omit them, you need to include the 2000 and then remove it later, so that at least you accommodate such numbers like 2010. It is even and it's greater than 2000. Right? And remember, I said this is the only approach. So problems of this nature, at times you cannot run away to include, then subtract. You have to do it that way. So the 4-digit codes greater than 2000 is no longer equal to 2000. It's strictly now greater than 2000 and even. We take this number and subtract 1, that is removing the 2000 that we have seen that it is possible we have it, right? So this is the answer to the solution. And this is the only approach you can do. Include, then remove. Right, let's go to D. What is the probability that a code will contain at least 1 7? the digits may be repeated, right? The approach that I'm going to do here has nothing to do with the tables, but it has to do with the idea of saying it contains at least 1 7. So the question would be, do we have such digits or codes with the digits without the 7? Right. So first and foremost, let us find our possible arrangements of the digits, coming up with the 4 digits codes. We are saying since we have 8 digits to deal with, repetitions are allowed because digits may be repeated. So it's 8, 8, 8, 8, right? So the possible 4 digits codes set S, right, is 8 to the power of 4, right? We found that in 8 before, right? So that means in this set 8 to the power of 4, we have it codes without the 7 and with the 7. That is what it means, because it's possible we are going to have some codes without the 7 and some with 7 or more 7s, isn't it? So here everything is in. So the next thing is I'm going to remove the 7 aside, then come up with 4 digits codes using the digits 0 to 6 only, right? So this is the situation. There are now 7 digits. 7, I've put it aside. So first position, I'm still obeying the issue that the digits may be repeated. So first position, I can have the 7 and so on up to the end, such that now the result of doing this, we are simply saying possible 4 digit codes without digit 7. I've removed it. Then 0 to 6, I'm using 7 digits, right? So it will be 7 to the power of 4. 7 times 7 times 7 times 7. So this result, we don't have any 7 in it, right? So if that is the case, a result without any 7, a result with those codes with 7 and without. Therefore, if I remove this from this, I'll remain with the number of codes with at least 1 7. So for the favorable 4 digit codes with at least 1 7, set F, it is equal to 8 to the power of 4 minus 7 to the power of 4. That means this minus this, and I've explained why, because this is as a result of making 4 digits code without the number 7 itself. It's not there. We are only using 0 up to 6, and we have this. But with this one, it's including everything. So if you subtract this from this, we are getting the 4 digits code with at least 1 7. So if that is the case, now we have our possible outcome and the favorable outcome. So since we want the probability that the code will contain at least 1 7, therefore we have the number of favorable outcomes over the number of the sample space, which is equals to this, which you have seen, that's our favorable number of outcomes over the possible outcome, which is this. This reduces to this fraction. However, this is not the only approach. Alternatively, we could have used the idea of probability of complementary events, right? That is, probability of at least 1 7 is equals to 1 minus probability of no 7, right? We are talking of probability of no 7, right? So the probability of no 7 is, here we have the favorable outcomes. there is no 7 in here, right? So the probability of no 7, it will be 7 to the power of 4 over 8 to the power of 4, which is this one. That is 1 minus 7 to the power of 4 over 8 to the power of 4, which is probability of no 7. It's probability, right? Then when you subtract this, you get this figure. So this is how I thought I could do this problem, because it becomes very straightforward when you think in terms of complementary events, or the idea of removing the 7 and trying to come up with the possible combinations of the digits to give a 4-digit code. Okay, number E, what is the probability that a code will contain at least 1 7? The digits may not be repeated. Otherwise, the D, we are repeating the digits. Here we are not repeating the digits. That is the only difference. But otherwise, the approach will remain the same, that now my possible outcome, I'll do it without repeating any digit, right? So it will be the first. Once it's filled, I'm left with 7. Once it's filled, 6. Once it's filled, it's 5. Using the fundamental counting principle, we are saying the possible 4 digits code set S is 8 times 7 times 6 times 5, right? Once I'm done, now I'm going for the idea of at least 1 7. In the similar way, we approach the one in D to say, let us find the possible outcomes without a 7. That is making use of digits 0 to 6, right? So we are saying the first position, all the 7 digits, 0 to 6, can occupy that. Once it's occupied, you are left with 6. Once it's occupied, 5 up to 4. And by fundamental counting principle, we are now saying possible 4 codes without digit 7, because I removed it, right? We have 7 times 6 times 5 times 4. This is what we have. Now for our favorable 4 digits codes with at least 1 7, which we call set F, then we are going to say the possible outcome minus the outcome without the 7 to get at least 1 7 in the other numbers for the other codes. So this is all what it means. This is this part minus this one without the 7. So will give us 4-digit codes with at least 1 7, right? Therefore, the probability that the 4-digit code will contain at least 1 7, no repetitions, number of favorable outcomes over number of possible outcomes. Our favorable outcome is this, right? Set F, which is what I've copied here, over the possible outcome is this set S, which is this. This simplifies to 1 over 2. Alternatively, if you consider the probability of complementary events, we are saying probability of at least 1 7, no repetition, is equals to 1 minus probability of no 7, no repetition. That is 1 minus probability of no 7. It will be the favorable, that is this part, 7 times 6 times 5 times 4, right? Over the possible outcome, which is 8 times 7 times 6 times 5, which is what we have. Remember, this is probability of no 7, which is this one. We subtract from 1, again, we get half. So this is maybe wherein the idea of using the columns and the row, it's important, but the thinking pattern should be guided by the actual process that we are carrying out as we are coming up with the codes. Because the at least one, that means the codes, I should have a 7 there or more than 1 7. That is what it means, right? So by then trying to come up with a possible outcome, including the 7, then remove it, then subtract to actually find the at least 1 7 is very important. Okay, let us go to F. How many codes can be formed between 4,000 and 5,000? The digits may be repeated. We still have our 8 digits, 0 to 7, right? Now we want to know the number of codes that we can form between. The word between simply means the code should be greater than 4,000 and less than 5,000. That's the meaning of between. It cannot be 4,000. It cannot be 5,000. No. So 4 digits codes, let's say they are represented by X. So we are saying those codes X should be between 4,000 and 5,000, right? This means that the only first digit for such numbers is 4. That is all what it means. We have to start with the 4. It cannot be 5 or less than 4, right? When it's greater than 4, then we are saying it's 5, but it cannot be 5. So it is 4, which is less than 5, right? So that's the first digit for such 4 digits codes that we want to be between 4,000 and 5,000, right? That said, all what it means, since we only have 4 as our only first digit, so we put the 1 here to represent 4, isn't it? Then once this is filled, the second position, since repetitions are allowed, we are still using all the 8 digits. So then we have 8, 8, 8, right? Again, we need to take note of, as we do this, the fact that there are repetitions, possibility of getting 4,000 is there. So the 4 digits could equal to 4,000, but less than 5,000. I've put equal to 4,000 because it will come up to, because if I put a 4 here, then 0, 0, 0, I have that 4,000 is there, right? But it cannot go beyond 5,000. No, because that's the 4 that is starting here, right? So it is 1 times 8 times 8 times 8, which is this one, which is 512. But remember, equal to 4,000. But we don't need, we need between 4,000 and 5,000, right? Therefore, the 4 digit codes between 4,000 and 5,000 is 512 that we have seen, including the 4,000 minus 1, we get 511. We have excluded the 4,000. It's not part and parcel of what we want. We want the codes to be between. That means it should be greater than 4,000, but less than 5,000. So this is the approach that, for me, I don't think I was trying to think whether I could get another way of doing it, but this is the only way you can do it, because at the end, you can't afford to miss the digit 4. The fact that you are saying between, then you say, I cannot use the 4. Then what are you going to use now? So the 4 should be the only first digit. But as you do that, since the repetitions are allowed, then you are bound to get a code which is 4,000, but we don't need it. Then Once you have that figure, you have to subtract 1 to actually come up with the 4 digits codes that are between 4,000 and 5,000. So this is the answer to the problem, 511, right? We have excluded the 4,000, right? So these are the tricks that always come with this type of problems wherein you want to come up with the codes. And this is the approach. And I don't think there's any other approach besides including it, then removing it. Kudos for watching.